Hi, everyone. Thank you for joining us today, and welcome to our webinar, Effectively Use Geospatial Data in the Disaster Management Cycle. I'm Jody Lee with L3Harris, and I'll be the moderator for this webinar. So before we get started, just a couple of housekeeping items. I've muted the phone line for all attendees, so if you have any questions at any point during the webinar, feel free to enter them into the Q&A box, and we'll try to answer as many as we can at the end of the presentation. We are recording this webinar, and we'll have it up on our website at www.L3HarrisGeospatial.com in the next couple of days, hopefully tomorrow. We'll also email you a link to the recording as well as the slide deck, which you're welcome to share with your colleagues. Next slide. If you're not familiar with L3Harris Technologies, I'm just going to take a few minutes to go through who we are. So L3Harris Technologies is a global aerospace and defense contractor who delivers end-to-end solutions that meet our customers' critical needs. The company provides advanced defense and commercial technologies across air, land, sea, space, and cyber domains. We have about 48,000 employees who are located in approximately 30 different countries. Next slide. So within the L3Harris Space and Airborne System segment is L3Harris Geospatial, where JP and I work. We're the leading provider of software solutions to extract meaningful information from all types of remote sensing data, including synthetic aperture radar, LiDAR, and optical systems. We offer end-to-end solutions, geospatial solutions, from data collection and dissemination, to analytics and deep learning capabilities, to custom solutions, in order to help our commercial and defense customers solve hard problems and make better decisions. L3Harris Geospatial also offers the largest selection of satellite and aerial imagery, elevation data, and more. For those needing unique requirements, we have a team of experts that provide custom services that meet our client specifications. Next slide. Okay, so now the reason why we're all here is disaster management. I'm excited to be joined today by JP Metcalf, one of our sales engineers at L3Harris Geospatial. JP's only been with L3Harris 1 year, but has made a big impact already. He has a Bachelor of Science in Geographic Information Science and a Master of Science in Remote Sensing Intelligence, and has definitely done a lot of research in the field over the years. So without further ado, I'll turn things over to you, JP.
Thanks, Jody. Hello and welcome, everyone. Welcome to the webinar for effectively using geospatial data for disaster management. Adding on a little bit of a background, I am a sales engineer and I work primarily with commercial. I started off my career in the US Navy as a strike intelligence analyst on board the USS Nimitz way back in around 2001 to 2005. And that mostly involved photogrammetry and high resolution imagery. I stuck with that and then did my undergrad at San Diego State in GIS, got really into remote sensing, and then I went on to Naval Postgraduate School in Monterey around 2011. And then after school, master's, I worked there for about 10 years as a faculty associate. And during that time, I eventually started teaching optical physics for remote sensing, and primarily got into LiDAR intensity and waveform research, a little bit of photogrammetry with UAVs and hyperspectral. All right, let's get started. So we're gonna go over a little bit of intro material, and then we're gonna talk about 2020, a year in review for disasters. Disaster management cycle will be introduced after that. That includes mitigation, preparation, response, and recovery, so 4 phases. Go into case studies that apply to each one of those phases. And then we'll talk a little bit about the new disaster website that we have at L3HarrisGeospatial.com. And then we'll take questions. All right, let's go over the background. Last year, The entire globe was focused on combating the COVID-19 pandemic, leaving very little room to mentally prepare for disasters to come. Still going to have natural disasters. The graphic shown here comes from the United Nations Office for Disaster Risk Reduction, illustrating the numbers of non-COVID related disaster events by continent and by the top 14 countries. Overall, a total of 389 disaster events occurred in 2020 alone. The Asian continent experienced the highest numbers of disasters at 161 events. Indonesia accounts for 29 of those, where 25 of the 29 were flooding. India and China experienced lower event numbers, but suffered the largest human impacts with 19.6 million people and 14.9 million people affected respectively. In the next few slides, the report on disasters in 2020 breaks those numbers down by disaster type, number of deaths, and economic loss, and then compares those to the average number over the past 2 decades. So the year 2020 experienced a slightly higher number of total disasters when compared to the annual average from 2000 to 2019. This chart shows that the uptick in total events was mainly from weather-related disasters like flooding and storms. There were 23% more floods in 2020 than the annual average of 163. And there were 26% more storms than the annual average of 102. You notice that the proportionality of the counts by disaster type along that bottom part remains relatively the same from 2020 to that average between that 2 decades. The number of deaths was way lower for 2020 than the average for the previous 2 decades. Extreme temperatures were the deadliest type of disasters, accounting for 42% of the total amount of deaths, followed closely by floods, which accounted for 41% of total deaths for 2020. Summer heat waves in Europe were the deadliest events for the 2nd year in a row. And with 30 named storms, got into the Greek alphabet, the 2020 Atlantic Ocean hurricane season broke the record for the highest number of named storms. Hurricane Eta, ETA, was the most impactful of these storms, killing 394 people and affecting 7.1 million people in 10 countries. And that's stretching from Colombia to the United States. Overall, the economic loss in billions of dollars was higher when compared to the 2-decade average. The chart shows that flooding and storm damage are some of the highest costing types of events, which I'm sure is related to their frequency. In a year of record-breaking storms and wildfires, the Americas suffered 53% of total economic losses, largely in the United States, which experienced the bulk of the year's most costly climate-related disasters. So let's talk about the disaster management cycle. Emergency managers think of disasters as recurring events with 4 phases, and that's mitigation, preparation, response, and recovery. The graphic on the left shows the relationship between the 4 phases of the disaster management cycle. And an important thing to note is that all communities are in at least one phase of that cycle at any given time. The mitigation and preparedness phases all occur prior to a disaster event, while the response and recovery phases occur post-event. Remote sensing imagery, whether from land, air, or space, can play a large part in the ability to inform emergency managers during each stage in the disaster management cycle. And we'll talk about that. So here's some variables to consider. In order to effectively utilize remote sensing and geospatial data in disaster management related projects, it's important to understand the time constraints for project completion, as well as the availability of data and resources in order to maximize the benefit to disaster management organizations and their personnel. For example, a project involving the determination of fire-prone areas might first evaluate the modalities of remote sensing that are better suited to map fire-related variables. Then, once you've settled on modalities, you can allocate the time, the cost, and the resources needed to process the data and disseminate information in time for mitigation activities to occur. So there is a relationship between the time you must complete a project and which stage of the disaster management cycle your project area is in. Prior to an event, you can allocate much more time to accomplish mitigation efforts, such as mapping flood-prone areas. The available time starts to condense just prior to an event where information needs to be disseminated very quickly and widely as possible. Early hurricane warning is an example. Just after the event occurs, information relating to search and rescue is much more useful if it's released quickly and accurately. And then in the recovery phase, a longer amount of time can be devoted to imaging larger areas. And then that can help determine the extent of damage and monitor recovery. So the availability of remote sensing data mainly revolves around altitude. There's a high availability of imagery and frequent revisit rate that's often related to spaceborne sensors. Multispectral satellites in the geobelt, such as GOES, are useful for detection of hurricane formation and missile early warning, as they have frequent views of the entire hemisphere, but at the expense of spatial resolution. We're talking kilometer-sized pixels. The sub-meter to a few meters resolution imaging satellites are found in often a sun-synchronous low Earth orbit. The high spatial resolution satellites are often large, very large buses, having revisit rates on the order of days. To get the revisit rate down, constellations of small multispectral and SAR satellites, such as Planet and Capella, have been going up in the recent years, allowing daily to near daily revisit, which is good for monitoring that phase where it's prepare and respond, where you need that high revisit. Satellite hyperspectral sensors do exist, although their spatial resolution can be quite low when compared to their multispectral counterparts. So there's a relationship between the temporal resolution, which is the revisit, and the spatial resolution, how small a pixel can be, and the spectral resolution going from multispectral to hyperspectral. So real quick, here's one of the latest GOES East images of the continental United States. It shows Tropical Storm Elsa making its way to Tampa Bay area as of 6 July, so a couple days ago. It was classified as a hurricane previous, but by the time it hit land, it's considered a tropical storm. In the graphic, water bodies and land are shown as grayscale, where the water is very dark and the land is very bright. The National Oceanographic Atmospheric Administration, or NOAA, releases these loops called sandwich products, which are a combination of visible and infrared bands to show high resolution and the temperature. This loop in particular covers 2 hours and is made up of 24 images. If you go to their site at star.nesdis.noaa.gov, you can download even longer loops and then save those as GIFs. Those are pretty fun. All right, let's get into mitigation. In the mitigation phase, it's important to understand the risk given to an area so that strategies can be developed to try and prevent or at least lessen the impact to people and property. Some examples of the mitigation phase are to create inventories of things like critical infrastructure or forests, monitor elevation changes in urban areas like subsidence, and understand how landscapes change over time with frequent monitoring. So one of my first examples for mitigation is the continuous analysis of crop health is achieved with multispectral and sometimes hyperspectral sensors. Depending on the size of the cropland, the complete failure of a crop can have a large effect on a local population. The crop science module, developed in ENVI, is made to delineate and track the health of fields, both small and large, over their entire life cycle. In this example, individual trees of a citrus orchard were vectorized from airborne imagery, and their NDVI values were computed for each tree. The gradient on the left graphic on the bottom right, the gradient from red to green shows how well a tree is doing compared to the rest of the orchard. With the higher spatial resolution coming from airborne and UAV platforms, Individual plants can be delineated and their performance within a field can be analyzed using hotspot analysis. Notice that in the bottom right, I've included some visual metrics on data and resource availability, as well as time to complete for this case study. And I've included them for some of the rest of the examples. So in this case, I brought up airborne imagery, which is more leaning towards a commissioned, we have to pay for this flight type availability scenario versus satellite resolution. The next example is power utility companies. It's important for them to monitor the encroachment of vegetation on power lines and power poles, as well as making regular maintenance on that equipment. Encroaching vegetation not only is hazardous as a source for wildfires, but the subsequent power outage can result in a whole host of issues, such as livestock loss due to a lack of refrigeration. Aerial LiDAR collection along corridors can help with mitigation from providing highly accurate point measurements in X, Y, and Z on the power lines, the power equipment, and the surrounding terrain. Automatic extraction algorithms and LiDAR point cloud focus software, such as ENVI LiDAR and Amplify, can extract power line and power pole objects to determine metrics like line sag and pole lean. On the left, within that yellow cylinder, points colored red are encroaching within 10 feet of that power pole. This customer in particular wanted to know if any poles were leaning in excess of 5 degrees. And in this case, that pole was found to be 8 degrees. And beyond the LiDAR capability, you can also collect high resolution oblique imagery using UAVs that can fly very close to these assets and determine whether they are damaged or not, and also the type of equipment using deep learning models. I'll talk a little more about deep learning in a second. So I mentioned forest inventories. They lend themselves to the mitigation process by determining metrics for fire modeling and prediction. LiDAR works particularly well for forest inventory since the laser light can often penetrate the forest canopy. And I say often because it really depends on the density of the forest, characterizing the terrain where other modalities would have a hard time seeing the ground. You can also automatically extract individual tree height and their crown diameters with the use of feature extraction and ENVI LiDAR. Two extremely useful raster products derived from topographic LiDAR are the digital surface and elevation models, or height maps. And you can produce those for both the terrain and the canopy. If you subtract the elevation model from the surface model, you obtain the normalized tree height. And then adding tree health is as simple as fusing multispectral imagery, such as Sentinel-2, with height data, and then producing NDVI metrics for each tree. Also, in July of 2019, a highway near our office in Broomfield, Colorado, had a major collapse. Cracking was seen the night before, so the lanes were closed prior to the collapse, which is good. Good that it was closed, not that it was not good that it collapsed. Curious as to how this happened, a colleague examined 30 SAR scenes from Sentinel-1 going back to the previous year, and then leveraged ENVI SARscapes, small baseline subsets, and then persistent scatterers, and did that processing to determine the vertical displacement over time. The graphic on the left is showing movement over time in millimeters and towards the direction of the ascending and descending nodes that were used for those SAR scenes. The large lake bed in the voided area was found to have an upward displacement, while the highway overpass adjacent was found to have downward displacement. Major movement on the highway towards the lake bed was found to occur in April, which is approximately 4 months before the collapse. So like I was saying, this is the collapse happened, and then we had to figure out, how did this happen? Can we monitor this? So the work was done after the collapse, but it would be much more beneficial to monitor this over time prior. Now we're in the prepare phase. The preparation phase includes planning, training, and educational activities for events that cannot be mitigated. Examples include detecting early stages of drought, hurricanes, and floods, mapping the quickest routes to safety, and designing early warning systems in order to disseminate information in the right places very quickly. An earthquake strong enough to potentially trigger a tsunami affecting Australia occurs on average about once a week. Within minutes of an earthquake striking, seismic data relating to the earthquake is loaded into a tsunami decision support tool at the Joint Australian Tsunami Warning Centre, and that's hosted by the Australian Bureau of Meteorology and Geoscience Australia. Residents of coastal areas have less than 30 minutes to prepare for those waves that might come ashore once that earthquake does occur. This software was made using the interactive data language, IDL, that is a programming language that is complementary to ENVI. And with that software, automated messages are generated through email, text, and Twitter, showing dynamic web maps where the tsunami is likely to form and where it might hit. The calculation of fire safety zones are used to determine where you can approach and fight fires without getting burned. This example compares the flame height to the same safe distance you can stand from it. To develop safety zones within a fire area, we combined aerial LiDAR and Sentinel-2 imagery. The calculation for the safe zone is basically 8 times the height of the vegetation, and that height comes from that LiDAR data. Go over a quick workflow of what that looks like. So on the left, you have a LiDAR point cloud over a forest area. Then you want to create a digital elevation model and its surface model. And if you subtract that elevation from the surface model, you get a canopy height model. And then with ENVI Crop Science, you can determine the locations of each tree using the crop count tool. And on the side, if you take that Sentinel-2 image or whatever multispectral image that has infrared information or that you can produce in DVI, you can fuse that with the tree locations and produce health. And then with that 8 times the height of the tree, you can produce safe separation distance maps. So you can use these to prepare for if there is a fire, that you know where that you can ingress and safely fight these fires. On to the response phase, which occurs in the immediate aftermath of a disaster. During the response phase, businesses and other operations do not function normally. Examples of effective response is to rapidly assess the severity and impact of damage, identify risks of secondary damage to the community, and provide real-time situational awareness to disaster responders. Here on the left is an 8-band Worldview 2 image collected over the Hawaiian Kilauea eruption in 2018. In the red, green, and blue composite on the left, the lava plume is clearly visible, but mixed in with those clouds. The hope was that we could classify the molten lava, the dark previous lava flow, and discriminate the plume from those clouds. On the right, the upper right, a false color composite with the near infrared channels from that 8-band image was found to highlight the active lava flow very well. And then after radiometric calibration and pan sharpening and atmospheric correction in ENVI, a deep learning model was produced to classify those 3 lava-related classes. The bottom right shows the results of that classifier. It did a great job of defining the active lava flow in that peach color. And now what is hard and cold lava is in blue. And then we have that purplish color with the active gaseous plume. And we see that the white clouds are still white, so it wasn't classified as gas. Another deep learning example. In March of 2020, a tornado went through Nashville, Tennessee, causing lots of residential damage. Just after disasters like this happen in the United States, National Oceanographic and Atmospheric Administration, or NOAA, will often collect nadir and oblique aerial imagery and disseminate the mosaics for public consumption. It's very nice of them. At 15 centimeter spatial resolution, building damage is readily apparent, so a deep learning model was trained using that aerial imagery to identify damaged buildings. And then using IDL, that programming language I mentioned earlier, The tornado path can be illustrated by fitting a least squares line along the highest density of those damaged buildings. And then in August 2020, the derecho that hit Iowa resulted in severe economic damage. And if you haven't heard the term derecho before, it's a Spanish word for straight. And in this case, it's a straight, widespread, long-lived windstorm that is associated with fast-moving groups of severe thunderstorms. It's the first time I heard of derecho for quite some time. In this example, images from Planet 2 were downloaded from before and after the derecho. And then a deep learning model was trained to determine the extent of crop damage, and that's shown in red. And you can see the path of this straight line storm. In the recovery phase, we focus on actions to return an area to normal, or at least near normal conditions through rebuilding and rehabilitation. This requires gathering information, understanding where the greatest need is, prioritizing work, distributing resources, and then monitoring the recovery. Long-term recovery includes restoring economic activity and rebuilding community facilities and housing. First example of recovery would be an intense tropical cyclone, Idai, and I could be saying this wrong, Idai, was one of the worst tropical cyclones on record to affect Africa in the Southern Hemisphere in March of 2019. The long-lived Idai brought strong winds and caused severe flooding in Madagascar, Mozambique, Malawi, and Zimbabwe, which killed at least 1,300 people and affected more than 3 million. SAR intensity time series from Sentinel-1 is very useful for showing flooded areas. The intensity of the signal return can drop as most of the signal has been reflected away from that smooth water surface. So I mentioned time series. It means collecting many images over time. So when you have what an area looks like prior to a flood, and then you compare that to a new image that shows all these dark spots, you can start to make inferences that something's happening here. And in this case, that the return signal is showing that we have water flooding. And then in this example, 3-band imagery from that NOAA website that I mentioned was acquired, showing the aftermath of the Joplin, Missouri tornado in the May of 2011. Nearly 7,000 homes were completely destroyed, and 875 homes suffered minor to severe damage. Damage categories present in the imagery included surface and structural damage, rubble piles, and blue tarp. And then using our deep learning module, these spatially and spectrally complex categories were quickly labeled in a few subset images. And then a model was trained in under 30 minutes to then identify these classes in the other larger tiles. And when I say larger tiles, they're about 14,000 by 14,000 pixels at 15 centimeter resolution. The output classification image is shown on the bottom left graphic, where the tornado path is again, it's pretty apparent. And I say spectrally and spatially complex. If you think of a pile of rubble, spectrally, it's going to be a mix of a bunch of different things. But when you look at a bunch of damaged homes and you see piles of rubble or garbage or rooftops on the ground, you know in your mind that is rubble, and it's not it's not just garbage buildup from somebody not cleaning up, right? And you put all these things together in your head and you say, right, this is a pile of rubble. That's kind of what we're doing with deep learning, and that's why you hear about it so much in this disaster management. And then something I'm working on right now is the ability to delineate tarps across the entire data set. And so the way I did this is on that storm site that I mentioned, is you can look at WMTS layers, which makes viewing a whole bunch of imagery at once very simple. And then you can determine whether you want to download that. So I used it to find whether there was very visible post-damage or post-event damage. And I found a ton of blue tarps and also green tarps. So what I did is, from that previous example in the tornado damage, there was some work done to already find these tarps. So I took that model and began to classify a few chips or a few tiles. And then it didn't quite work as well because I have these green tarps in there as well. And I also had these backyard blue pools that were getting confused with this. So what I did is I took those classification images and then I cleaned them up a little bit, and then I refined a new model. And I did that on about 6 of those larger tiles. Like I said, they were about 14,000 by 14,000. And I did this on Amazon EC2 to take some of the, or at least relieve my laptop from overheating. Deep learning takes a lot of resources. So it takes about an hour to actually create the model, and then another 48 hours to classify every single one of those tiles. And there's about 1,200 tiles here. So that's for Hurricane Delta, and that was in October 2020. And what I also found out, if I just looked at the previous couple hurricanes, that Hurricane Laura came through this exact same area, which is Lake Charles in Louisiana. And then I wanted to figure out if the tarps were already there after Hurricane Laura and still present in Hurricane Delta, or this Hurricane Delta is causing new damage. So this work is still ongoing because it takes a lot of processing, but I will be presenting this work at the ESRI user conference coming up in a week. So you're welcome to join me with that. We do have a new disaster management focus site, which is located on L3HarrisGeospatial.com. If you go towards the top under industry solutions, you'll find disaster management. Inside, we talk about a lot of what we went over today and how disaster management cycle applies to all different types of disasters beyond what was discussed today. Also, if you head over to that site, you'll find a wealth of disaster-related information from just the last year in the form of past webinars, white papers, case studies, and even informal videos called geospatial distancing. And that started up when COVID-19 hit. You'll notice that from some of the titles that SAR and deep learning processing are becoming frequent topics applied to disaster-related work. And I have all these linked, so when the PowerPoint goes out for this, you'll be able to click on these instead of trying to search for them all. We also have a 30-day no-risk free evaluation of deep learning, which you can find on our website. Once again, my name is JP Metcalf, and my email is jp.metcalf@l3harris.com. And I'd be glad to take any questions.
Great, thanks JP for the presentation. I loved all the different examples and how you use the software and technology to help with each of these things. So that was great. And just a reminder to everybody, we are recording this, and so we will email you tomorrow with the recording and as well as the slide deck, so you'll get that. We'll also have it up on our website at www.L3HarrisGeospatial.com tomorrow. So at this point, we're going to address some questions that have come in. If you do have a question, submit it into the Q&A box. The first question: how can we leverage the mass proliferation of small drones to fill in gaps in the disaster management cycle?
The mass proliferation of small drones to fill in gaps in the disaster management cycle? Okay.
Yes.
I didn't get an opportunity to talk about drones or UAVs quite as much as what I wanted to. But basically what happens is these are very quick to get up in terms of response and collect very high resolution imagery. There are avenues to be able to upload that imagery, even if you're just like an amateur photographer, to sites like Open Drone Map, and then that imagery can be utilized. but they're very good for making mosaics and photogrammetric processes to produce that 3D information that I mentioned about with forest and LiDAR. So to fill in the gaps is basically, when I mentioned satellites and they have a revisit rate, you basically have to wait for some of these satellites to revisit before you see anything new. Also, if it's a visible satellite and it's an area where we're talking about hurricanes or thunderstorms, that this is often associated with clouds, which would be very hard to see through. That's where SAR comes in. Or if you get underneath the clouds and you have your drone that you can get up very quickly, very portable, then you can start to collect information and as well as video on whatever your feature of interest is.
Great. I can answer this one, but people are wanting to know if they can get a certificate of attendance for this webinar. And if you email us at events@l3harris.com, then we can send you a certificate. Another question, I was wondering, who are the users for the results such as the Cyclone Idai flood detection?
Who are the actual users?
That's what that sounds like.
Oh, okay. Well, I mean, on a broad general note, that that would be the responders or the governments of those areas. The work that we did was I would have to find that out of who the customer was.
Okay.
Also, here's another one. Did I try to classify video using deep learning? I have not tried to classify video. I don't see why it would be an issue. The video wouldn't be an input, it would be individual images. There's a satellite called Satellogic, which I have some data, and that produces video. And I've always been meaning to classify that time series. But deep learning does work very well on time series as well.
So I don't know if you can answer this, but some people are wanting to know, like, how can they access some of the data? So API, console, S3.
Oh, right. Yeah, so I mentioned one of my current works right now is to pull down all that NOAA imagery, which can get very large if you're working with the raw data. They actually host that on S3. The way I've been interacting with it is at least looking at it. And so I have a local copy, but that's from S3 to S3. So that work was done on EC2. Otherwise, you can access those WMTS imagery, basically repositories that show these large collections of images. And if you want to just look at an area and find out if it has a certain type of damage just visibly, WMTS is perfectly fine. Or if you want to do some kind of scientific analysis, let's say an ENVI, you would need to download something like that.
All right, next question. Did you try to classify videos using deep learning?
Yeah, I answered that like a second.
Okay.
Right before that, yeah, right before that one.
Sorry. Can ENVI ingest locally collected LiDAR data?
Absolutely. So LiDAR data often comes in LAS format, or at least it's a standard. It can be in text or BPF or NITF. ENVI LiDAR is more suited to ingest and process LAS files. ENVI software can open LAS files. It's preferred to rasterize it first. Here's another one, is why is the phase respond? Why does that come in third place in disaster management cycle? Well, it's not necessarily third, it's a cycle, right? But respond is after the disaster event. So the way I talk about it is that there's two phases prior to an event, and that's mitigation. That's that long baseline period that you have to start looking at and tracking changes. And then you have that very short amount of time right before the event, like prepare. Like this would be like goes, right? So you see these cells forming out in the ocean, and then you have a limited amount of time to prepare for something that you can't really do much about, right? Like that hurricane's gonna happen. And then respond is directly after the event.
Here's another question. What is the maximum, I just lost it. What is the maximum image capture and analysis frequency for a specific area? The maximum image capture and analysis frequency for a specific area.
The maximum?
Yeah.
It depends on what sensor you're talking about. So I can give a couple examples. If we're talking about UAVs, I mean, the maximum is how much battery and how much data storage you have. Like I did mention, like these things have 4K video. If we get higher up in altitude with airborne, either LiDAR or imagery, it's as much fuel and data storage and money you have. And then with orbital, sun synchronous satellites, there's only so many images that you can store in a single pass. And those are usually dictated by some kind of tasking. I have one here. It's for disaster managers, is it easy and quick to use deep learning or visual interpretation? So the example I had with the tarps would be more on the phase of recovery. So if an insurance company wants to figure out how much money to allocate to a given area, they're going to want to figure out how many roofs do we have to replace or at least fix. To manually find all of those tarps, which was over 12,000, it would have taken me quite an amount of time. Especially if I wanted to determine the area, which kind of says how much roofing material you're going to need. That would have taken a long time manually. I mean, with manual effort, you could say, all right, there's damage to roofs here. But that deep learning model, once it's made, you can just, the next time a hurricane comes through, tropical storm Elsa, and that imagery is released through NOAA, I have the model already. I just have to say, go find all those tarps, and then it's done.
A couple people have asked this same question or similar question, but has our team been actively working with NOAA or the U.S. government for disaster mitigation and even like, global hazards and stuff? Like, have we been working with these companies?
Oh, absolutely. So if you think about things that we're concerned with, let's say it's climate change, and you think of it as like a disaster, a potential disaster. We've worked very closely with NOAA to monitor plastics in the ocean, and that's mostly with hyperspectral data. In different pockets of L3Harris Geospatial, we work with NOAA on different projects. Here's another one: is what modules or tools are necessary to implement to apply on fire cases? There's a bunch. So I was talking about NDVI, which is a good surrogate for determining kind of like the water content of trees and plants. If something that's really dry out, it's going to have a low NDVI value and could contribute to its fire fuel factor. There's the height, which is either a photogrammetric or LiDAR process. So tools like NV LiDAR are very good at extracting that height. Hyperspectral, you can be able to start to tell different tree species. SAR, anything with SAR is usually going to be in the NV SARscape realm. Another question is Is there any hyperspectral data available these days from satellite platform? Absolutely. There is Prisma, Prisma. Also, another company is, I think they just launched, and it's Orbital Sidekick. And how much does it cost to license a copy of NV Deep Learning as an academic institute? If you want, you can send me an email at jp.metcalf@l3harris.com, and I can get you in touch with the appropriate location and person to be able to discuss that.
Yeah, and we'll also have, if you guys ask questions, we'll have somebody follow up with everybody that asked a question. So.
Yeah, I'm trying to go through them all here. Can NV run on Amazon EC2? Absolutely, and I prefer it. You know, EC2 can sit right next to S3. I frequently work with LiDAR data. LiDAR data can get very, very large. There's another question up here. It's been here for a while. Considering sensors capable of balancing resolution with national coverage, which sensors do you feel provide the best balance of temporal, spatial, and spectral resolution, specifically for mapping wildland fire burned areas? SAR. I think SAR is great. It's not only does it see through weather, it's active and you can use it at night, but it also can go off angle really far. So if you're trying to cover one area in particular, and in another pass, it can go off angle pretty far to be able to capture that exact same area. In essence, a SAR satellite collects off angle anyway, off nadir at least. So like I said, there's constellations coming up. Go ahead.
Okay. Can SRTM images be used for watershed modeling?
Absolutely. So SRTM would be your elevation, and that's going to be at a given resolution. So your watershed modeling is going to be limited by the elevation resolution that you're using. So if it's 30 meters or whatever resolutions the SRTM comes as. What else do we have?
Have you ever used Sentinel-3 data for flood detection?
I personally have not. I primarily work with Sentinel-1 and Sentinel-2. And does L3Harris make any of these available data via web services? It's a good question. I know that we do have a group called MapMart that will put together and curate some satellite imagery if you're interested. As far as hosting like WMTS, things like that, I would have to look into that.
All right. I mean, so it seems like the rest are kind of like more narrowed and focused questions, so we can ask, you know, answer those offline, unless you see any immediate ones. But I think with that, we're going to wrap things up. So we appreciate everyone's attention on the line. We will be sending the recording and the slide decks to you guys tomorrow, and it will be up on our website. We encourage everybody to share it with their colleagues. So thank you, everyone. And thank you, JP, for your awesome presentation, and have a great rest of the day.
Thanks for joining, everyone.